So we're here. All right, so we're down to kernel debugging, and I've got a lot of demos. I'm slowly figuring out how this thing works. WinDbg is famous for being difficult to use, and I'm learning a few of the simple tricks, but it never gets too easy. I think you have to use it a lot to get used to it, but it is the most powerful debugger. It's the one they use at Microsoft. I think they wrote it at Microsoft. So anyway, WinDbg is essentially only a command line tool. For some reason, they put it in a window so they can pretend it's using the GUI, but it doesn't. And that makes it a little confusing, like GDB. OllyDbg is more friendly, but it just cannot do the kernel. OllyDbg can only do user mode analysis, the same thing with immunity, which is essentially the same thing as Olly. So, of course, debugging the kernel is not something that most people do if they aren't at Microsoft, because they got to be writing components of the operating system itself or drivers, the only people that belong in there, but we belong in there because malware goes in the kernel. And it goes in there to get more power and to hide from people who can't find it, because it's another whole level up of sophistication to analyze the kernel. And again, just like any other technique to make your malware more hard to understand, it wipes out another bunch of analysts. So device drivers are the main code that people add to the kernel. This is how Windows is designed. Since device drivers have to connect to the physical hardware, they have to run in the kernel. Userland code is not allowed to touch the hardware directly. And so drivers are loaded into memory and stay resident and just respond to requests like services. The applications do not connect directly to the drivers, they connect to the devices. This is one thing that is bizarre about Microsoft language. A device is not a physical object like a network card or a printer. A device is a software structure which is used through a few stages to ultimately connect to the hardware. So you create this thing called the device, the driver actually creates it, and then it creates a userland thing called a device, which your userland program like Microsoft Word can connect to and send it to the device, which then passes it to the kernel mode driver, which then passes it out to the hardware. So if you plug in a flash drive, Windows creates the F device object, and now you can send data to F, and it will go to the device, and then to the driver, and then to the physical hardware. And if you plug in another flash drive, it might use the same driver, it's the same brand of flash drive, but the driver will create a second device now called G. And they're both created by the same driver, and they're similar objects, but they're different in that they point to different hardware ultimately. So the drivers have to be loaded in the kernel, the way DILs are loaded into processes in userland. And remember, when DILs load, it calls DIL main, which is the setup program that prepares Windows to use that DIL. When drivers are loaded, it calls DriverEntry, which does the same thing, which prepares the kernel to be ready to use that driver. So DILs use the export table. Drivers don't. They register the address for callback functions. That's what DriverEntry does. It fills a table with callback functions so that the driver can then be accessed. So in a normal read request, your application will obtain a file handle to the device, then you'll call read file on that handle, then the kernel will process it, and the driver will then call back. So for malicious request, the most common thing you do is from the malware, you ask for device I/O control. This will be user space modules trying to get to a driver. And so here's how it looks, and this is the diagram worth understanding, because the most important thing here is to understand Microsoft's strange naming system. The general rule whenever you're understanding Microsoft names is that everything is named wrong. So you'll notice that the thing called kernel32 is not in the kernel. The kernel's in this box. The kernel32 is the userland DIL to lead to the kernel. And that's why it's named kernel, because you have to understand how Microsoft logic is. So your program sits up here. It calls kernel32.dil. That calls ntdil.dil. And that calls ntos kernel, which is the kernel itself in the kernel module. Then also in the kernel is loaded a driver, and there are kernel data structures which then go to the hardware. So that's what's going on. NTOS kernel is the kernel itself. It's also called NT in the debugger for short. That is the kernel, and drivers are loaded into it. In Linux, there's a similar issue with loadable kernel modules. It used to. This is why really old versions of Linux like Slackware used to be that every time you add more software, you have to recompile the kernel, because the kernel didn't have any way to change dynamically. But Windows does, of course. Just like you can add code to userland with DILs dynamically, you could add drivers to the kernel as you need them. And that is much more convenient and much more versatile and, of course, much more dangerous. So there's some malware that lives entirely in the kernel and creates no device object. So in that case, it gets pretty hard to find and pretty hard to catch. And that's why they say, there are rootkits that are essentially impossible to find. Although there are modern tools that can find them, they get very difficult to find. So NTOS kernel has the core for the OS functions. HAL is called the hardware abstraction layer. And I remember this years ago going through HAL, you often had to adjust it. Before we started using virtual machines, we're sort of using virtual machines anyway, because Windows expects to send certain API calls to get to the hardware and expects the driver to take care of that, so it never actually cares exactly what your hardware is. The driver is the interface between the real hardware and Windows, and there's another thing called the hardware abstraction layer, which makes the motherboard itself look like it's acceptable to Windows, sort of like a VM translator there. And there was, I remember, there were some Windows maintenance things I was doing maybe 8 or 10 years ago where the HAL was a big problem. I've forgotten the details, but in the heart. What's that?
Ghosting was the big one.
Ghosting's one, yeah. There was something else about changing 32-bit machines to 64 or something where it was a big deal. You had to make sure it had the right HAL. Anyway, HAL is hardware abstraction layer. And where's HAL? HAL's not showing up here. Anyway, sorry. All right, so I got a few icebreaker questions about that stuff. Grab one if you need one. That's the orientation with general Windows nomenclature. And now we'll get into specifics of how to use WinDbg in very simple ways. Well, let me take it then. No point putting it back in there. I sort of like putting the peanut shells back in.
No power.
Yep, well, I got to fix that. All right. All right. So what is it an application directly interacts with? All right, I'm quitting at 30. All right, you can interact with the device. That's what it's for. The device is the user-aligned object that your program can see. Something like maybe a drive letter. All right. What code loads into a process? All right, I'll quit at 20, I guess. I think I may all the answers I'm going to get. Or maybe not. All right, and that are DILs. That's what DILs do. Processes load DILs. That's the most common way you inject malware into them. To connect to normal libraries and run them. All in user land. When a driver is loaded, what procedure is called first? All right, I'll quit at 25. All right, and that's driver entry, analogous to domain. That's what prepares a driver for use. All right, which one of these things runs in user mode? All right, I'm quitting at 25. All right, and that's kernel 32, runs in user mode. All the rest of that stuff is actually in the kernel, except the one named kernel. All right. So there used to be an acronym for the 4 stages of Windows boot up, and the funny thing is they're all named wrong. It was ASB. Anyway, this years ago. It's still the same though. That's the general way to remember Microsoft names, is they always are the opposite of what they should be. All right. So in virtual machines, you can set up kernel debugging by creating a virtual serial port, which is kind of insane. You have to make named pipes, which are these strange objects that are sort of like files, but they aren't files, and connect them together. The book talks about using boot.ini to activate debug mode, but that is finally over, except for, I think, embedded devices. Even Server 2003 is gone. Boot.ini is over. That was the old days when Microsoft would boot up by going through text file. Now it goes to bcdedit, so you execute this command, bcdedit /debug on an administrator command prompt, and that's what turns on debugging these days, which amounts to the same thing, but Microsoft switched to a binary bootloader, which is really important in case you have BitLocker drive encryption. It has to have the information there to decrypt the drive, so it's no longer enough to just have boot.ini and the root of C. It needs to have 100 megabytes of room to put code to start your machine now. And part of the code that goes there is these settings, like whether you're booting into debug mode or not. You get WinDbg from Microsoft. If you don't carefully clear out all the checkboxes, you're going to be downloading like 2 gigs of junk here, and it would take forever. If you clear everything except debugging tools, it's really pretty small. It doesn't take too long. This was 100 megs, and on you go. So anyway, it comes from Microsoft, WinDbg. It's a software development tool. And now what we're going to do is use LiveKD. LiveKD is not able to debug a live kernel. To do that, you really have to have 2 machines, so one can be the boss and the other can be halting and moving forward step by step. And there's no way to simulate that in one machine that I'm aware of. There was a product years ago that could do it, but it's very strange and not maintained and too hard to use. But you can load it this way, and let me reload this thing, get everything clean. Don't save anything. All right, you just execute this program. I'll say no. All you do is livekd -w. And what this does is it makes a kernel memory dump, and then you view the memory dump in WinDbg. So you're seeing an image of the kernel, but not the live kernel. But it's so much easier that that's all we're going to do here. This is a way to get some of the features of WinDbg available without having to bother to connect 2 machines, which was very frustrating. Previous generations of this class, the students were all lost. There's a whole series of complicated commands, and they only work about half the time, and you end up pretty frustrated trying to get your virtual machines connected together. So now you've got a version of LiveKD of WinDbg running here, and you can do things like lm will list the currently loaded modules. And so this tells you everything in the kernel, and it is a long list, as you might imagine. So here is the start and the end of modules. This goes from address A9 to B2. That's WinDbg itself, and onward you go. There are more and more and more objects in here. Now you could do lm m nt, and this will load modules matching the name nt. And there's only one, and it's called nt. This is NTOS kernel. And it goes from 824 to 827. That's the kernel. And you can tell because it has symbols over here, because Microsoft has symbols to give it names, like all the known Microsoft modules. Now, if you want to learn more about a command, probably the most useful thing is .hh. So if I want to understand more about that lm command, you do .hh lm, and then you get this old graphical Windows 3.1 looking help page. These are, I think, running off chim files, I'm not sure. So here's like a general introduction with facts that we should know pretty much. And if you double click this, it will then tell you about the lm command. So the lm has options A, matching pattern, and then something called a capital M to match the pattern. I don't know the difference, I didn't really care. You can load from address, but now you can look for things matching a pattern, and you can put wildcards in the pattern. So this is actually pretty useful to go back here to learn how to do things if you get confused. But just like with GDB in the other class, the cool thing is to learn just a few useful ones to work with. So I can do NT star and get all the modules that start with NT, and now I get NT and NTFS and NT DIL, and on you go. You can get a variety of things, and we'll play some games with this now that it's running. All right, we'll get back to that. So there it is, that's how it looks. All right. They're all command line commands, but instead of just putting in a DOS window, which would have suited me fine, it's in this stupid GUI, but all you do is type in the bottom like an IRC chat client or something. I don't know why, but that's the way it is. So D will read from memory. D dumps memory. You can dump it as A to get it as ASCII, or U as Unicode, or D to just see double-bit words. You can specify a name of some symbol to dump, or you can dump from an address. So if I want to, let's play with this one. If I take this DA command and put it in there, that's going to dump in ASCII the data there. Looks like there's nothing there. I could also dump as hexadecimal words from there. Let's just do this. I think it's X. Let's give it a shot. Or else it's W. Nope, I guess it's not X. What was it? D. All right, fine. It's X in Linux. All right. And DD doesn't seem to work either. Neat. Okay. No, there it did work. Neat. Module load. Oh boy, look at it crash and die. Cool. Okay. We'll come back to this. I'm not going to struggle with that right now because that's pointing to some useless part of memory. All right. So E will edit memory. To write it, as you do in debugger, you put in a breakpoint, you change the memory, you continue, and you cannot do that in LiveKD. Because remember, we're just looking at a dump. For that, you really need the 2 machines and the full debugging. So it's cool, but we're not going there. You have arithmetic operations, just like you have in machine language. You can refer to things like, this is going to dump Unicode, the value at a 32-bit location pointer, and this is going to be the pointer, which is indirect addressing, extend stack pointer plus 3. So this would be looking on the stack for a text string in Unicode that's being passed in. There's something like a file name or something. You can set breakpoints, as always. You can go to the breakpoints. You can set breakpoints even with complicated calculations for where it'll do, and you can set, you have a series of commands and even things that execute when the breakpoint hits. So you can arrange conditional breakpoints and all that jazz with these commands. But we can't do any of that, of course, with LiveKD. All right, you can list modules like I showed you. This shows you all the modules. And this is as close as you get to having a memory map. So usually, if you want to get oriented, remember, the first thing you do is LM. This lets you see what you've got. So to read from memory, you can see the module NTOS kernel, which is cool, and I played with this a while through DD NT, and that will show you the first several bytes of NT, and then you can have DD. Now I wanted to control this, and if you do this L10, it will do 10 objects, which is 16 objects because it's hex. And it refers to object whatever size you're doing. And the way I'm doing it, I'm dumping these D objects, which are 32-bit words. This is the closest to what we do a lot in Linux, where you do x/9x or 20x. So, and you can change that number L10 to L20. We'll just dump more of it. So that's one way to go. And we'll play more with that later. All right. All right, so you got online help like you saw, which is quite nice. I'm getting used to it. One thing it doesn't have, like Linux man pages have, is examples at the bottom, and they would really help. If they just had 3 or 4 common examples for each command, that's usually the first place you look to solve your problem, but you can't have everything. There is useful information there, but it could be more useful. There are some online guides, and I just found a good one I'll show you later. This right here, this chapter 10M is where I learned a few new commands, like how to dump the registers. This was very hard for me to find out. And this is like the first thing I do in Windows is dump the registers. See, in full debug mode, there is a register pane, a window you can open that shows the registers live all the time. But you can't do it in this LiveKD as far as I can tell, but you can do it with R. So there are the registers. Now, of course, realize that under these conditions, the registers are almost meaningless because we're not really watching a live kernel going through EIP and all that. But anyway, I was sort of reassured to see something familiar in this strange environment. Here's EAX, EBX. Someplace in here is going to be EIP, I would think. Well, I'm not seeing it, actually. Where the heck is EIP? There it is, EIP. Good. My friend EIP. Now I feel like I'm on solid ground. All right. So, all right. Got some more eye clickers. Good. All right. Which one will set a breakpoint? All right, I'll quit at 25. All right, BP, of course. Some things make sense. All right. All right, which one will show memory as ASCII characters? I'll quit at 25. All right, that's DA for dump ASCII. All right. Which one shows all kernel drivers? Good. I'll put it 25 again. All right, and that's LM. It shows other things too, but among everything else, it shows you all the kernel drivers. All right. And which one will change memory contents?
When they stuck to 2 characters, they could name things pretty well. When they expanded to 3 characters, it started getting confusing.
Well, maybe, yeah. There's a big philosophy argument there. I mean, this is why past COBOL abandoned all this. All the commands are complete words properly spelled. They just messed, and if you think about it, all abbreviations will just get you in trouble. If you just spell it right, then there's no question how to spell it. Execute, things like that. You know.
Some of us can't spell right.
Well, yeah, but see, if there's going to be only one right answer, why don't you just stick to the same right answer that's in a dictionary? Then we don't need to like. Anyway, that was pretty clever. It totally did not win though. COBOL is gone. So this philosophy actually made some sense to me, but I think but only.
It's in very old.
Yes, yeah. Other languages did not imitate this philosophy. It was real strange to read, whole words, long sentences, you know. Anyway, so all right. Anyway, so.
You could get a pretty good high-paying job.
People have told me that, yes. They're even, I was actually looking, no, I don't recommend it as a career path, but I was actually doing it in class. We were looking for Fortran and COBOL, and there were like 5 or 6 jobs in California to hire you for Fortran and COBOL, but if you knew something modern like Node.js or Python or something, there's a lot more.
There's tons.
Yeah. Anyway, so then there's Microsoft symbols. You can refer to everything by hexadecimal memory addresses, but that gets old really fast, especially since this is the kernel, and almost all that code is written by Microsoft, and you're not really going to be debugging it. So then you can have names like this, create process address space instead of just a meaningless hexadecimal number. So that's cool. You can search by symbols. You can have module name, bang, symbol name. Things like nt bang, nt create process, that will be the Microsoft nt kernel module that creates a process, which is called by anything that wants to launch a process, and that's cool. So this is going to work as long as you have the symbol names loaded. So let's try a few of these. We're going to unassemble nt create process. And all right. And I think I'll do one, and then we'll look at the man page, or whatever Microsoft calls it. So here we're going to unassemble Windows NTOS kernel that creates a process. And there it is. You see a bunch of lovely assembly code. This is the beginning of the thing. And you see, by default, 8 lines of assembly code, because the default is to show you 8 of whatever you asked for. And what I asked here was disassembly, so I get 8 instructions, which is not 8 bytes or 8 times 4 bytes. It's however many it takes to make 8 instructions. Like this is a 2-byte instruction, a 1 byte. This is a 5-byte instruction, it looks like, 4-byte instruction, so on it goes. So if I wanted to control the amount, I'd do length 10, and now I will get 16 instructions because it's hexadecimal. And if I wanted to know more about that, I can do .hh and U for unassemble, and I'll get this glorious graphical help page. And my mouse is.
If you wanted like 15, you could do link F.
You could,
Okay.
absolutely. You only do that in sec. Here's the story. UB range, and here you can go to learn what ranges are, and on you go. Yeah, so let's do that. If I do ULF, then I get 15. Yeah, so now we can unassemble code, we can see raw memory, we can see ASCII, and we can hunt through the memory map to find things. So we got a lot of the essential ingredients here to track down problems. All right, you can make complicated breakpoints that will have a deferred breakpoint that will only happen when that module loads. And you can have this function, I meant will find the entry point of the driver. It's like a environment variable. So now you can make a breakpoint that will break when this driver loads and tries to run its driver initialization routine. And that's what you logically do. Remember, when you load a program in OllyDbg, it loads and puts a breakpoint before it starts, so it's ready to go. And this is how you would arrange the same thing to happen for a driver, because I'm writing this driver, for example, because I made the printer, and I want to see my driver loaded up, ready to go. All right, you can search with X. You can search using wildcards. So I can do NT create process. Let's try this, xnt create process. ntbang create process. This will find the particular thing named nt create process, and it didn't find it because nothing has that exact name. So if I'm tired of hunting for that name, I can just put wildcards in it, just like you would in a file name, star create process, and star. And now I've got its nt create process is the simplest one, and there are many other versions of it. PSP create process and MM create process, and on it goes. And each one of them has an address and a name, and you can learn more about them here. And if you look at how powerful this product is, it's clear how people use all these undocumented Windows features. You can figure out how things work without any Windows documentation in WinDbg. So you can find a closest symbol. You can start from memory address, and it will just read forward to find named addresses near that spot. So you can try to find what modules are called or what's a known process here. You can view structure information, and this gets really powerful. So you can do DT to view symbols, which show you what's inside a structure. And so you can find out what a driver object looks like with this one, DNT driver object. Let me try that one. DT, it is ntbang underscore driver object. So you can run this, and now it will tell you, this is how you can figure out what a driver object is. Even if Microsoft did not want to document this, they documented this one, you'd find here, this is the structure of it. This is a 32-bit pointer, this is an integer, here's the names of it, driver extension, Unicode string, here's the names of it. So you can pretty much figure out what's going on from these names. Here's the DriverEntry pointer to where the DriverEntry function is in there. And so I wondered after seeing that if I could do a device object without even looking anywhere. I wonder what would happen if I did device object, and it worked just fine. So you can see what those devices are. Remember, the driver creates a device. So you have a driver for USB device, and when you plug it in and it goes to USB recognition, then it tells the driver, okay, I actually have one, create a device. So it creates this memory structure with all this junk in there, and that's what creates the device. That's the thing that your Microsoft Word is actually using if you save a file on a USB stick. And you can figure it out, even if Microsoft doesn't tell you what's going on. You can see the names, you can see how big things are, you can play with it and figure it out. All right. So that's what I did there. Try a few of those. Let me shove this thing out of the way. Come on. All right. All right. And here's some examples in your book for the beep driver. It's always loaded. This is the thing that goes beep when you press a key and it wants to beep at you. So this is the structure of this thing. And down here, there's DriverEntry. This is where it's going to, DriverEntry. This is where it's going to go when it starts, when it first loads this device. So the DriverEntry function is called, and that's the point there. So remember we talked about this, if you're going to have a DIL, and you don't want to get fancy, you just put your malware right in DIL main. It loads the DIL, runs your malware, you're off to the races. You do the same thing with drivers. You would just put it right there. Then as soon as it loads the driver, it runs your malware, as long as you don't care about like actually doing anything or what damage you do to whatever processes are happening. You know, if you're just a slob, you just want to run your malware and get going. So DriverEntry is called when the driver's first loaded. All right, you can get your Windows symbols. They're cached locally on your machine, or you can download them. If you have to get them for the exact versions of Windows and Service Pack and everything that you're using, you get them from Microsoft. You can download them here in various packages. It stores them locally, and that makes it very nice. So that you get these alphabetical descriptions of things. All right, got a few more eye clickers. It looks like we might be able to finish this one all in one go. We'll see. Up here and here. All right. We've done that, haven't we? Oh, no, we haven't. Oh, okay. There's another set. Which one of these creates a breakpoint? Okay.
What have you done?
It's another kind of breakpoint.
Did you show us this breakpoint?
I did. In fact, I'll wait till 30. However, simple logic would probably work. All right.
We'll see if it pays off.
All right. So I mean, you unassembles things, X examines things, B makes breakpoints. So that's it. That's a breakpoint, and that breakpoint there, that is the I meant thing, which automatically finds, I think, the DriverEntry point. Or the I meant thing is a global variable that finds.
Yeah, the DriverEntry.
I think it's the driver entry point, yeah. All right.
I don't know if I hit the button in time.
Well, possible.
We'll see.
It's a cold, cruel world. So, all right. And, all right, which one will show you the assembly code at the entry point of a driver? All right. Oh, well, that's not quite as simple as I thought. I got to think a little bit. All right. And the example is fast fat. I guess that must be for floppies. Anyway. All right. And that is D, where you, oh wait, item D, where you unassemble fast fat. That's what shows you the assembly code. This would put a breakpoint there, and these other things would not go to the starting point. It's the IMENT that goes to the starting point. All right. Which one will show the type information for a structure? All right, I'm quitting at 30. All right, and that's the last one. Go to popular answer. This will display the type information for that object. All right. And then you could go here and look at the code for it, and it's not impossible to see how you could figure out how things work that way. All right. Which one will list all the functions in NTOS kernel? All right, I'll quit at 30. All right, and that's the one in the middle. And I bet it's a pretty long list. Let's go see. So here's X, NT, bang, star. That should be every function in the kernel. And there they are. Not an unthinkably long list, but a pretty long list, as you would imagine. Every bloomin' function. Compose, hang you, create section, resource timeout count, you know, just like sort of looking at the handles or the processes. It's a long list of complicated little doodads reminding you that computers are really big.
That's a couple million lines of code.
That's right. Well, it's yeah, I think you can see how big it is. Yes, it's.
That's like a good way to crash the computer too.
Well, it wasn't that bad. But yes, when I was working on that capture the flag contest with 67,000 files, I was careful never to open a GUI window showing it, because I'm aware that will crash, or at least slow down the machine to zero. That's why the command line is so much better. Command line is much more efficient.
In the Mac,
Yeah.
it would try and thumbnail all of them to their actual text in the thumbnail.
Oh yeah, I don't know if a Mac would be any better.
Yeah.
It's a good point. I did not open it in the Mac either. This is why God made the command line. So, all right. So anyway, a little bit here about in practice. So you got kernel and user mode functions. Kernel mode programs cannot call user mode functions like create file. They would have to use NT create file. And he has an example here which seemed a little contrived to me, where if you have a kernel rootkit that wants to call the user space file writer, you could do it, but it's of course complicated. I'm not sure why you would. But you do it by creating a service, by calling this thing create service with the right parameters, and then you create a file here with this file name being set to this space backslash file writer backslash device. The service is, I think, called file writer, and you call that service. That's how you do it. Anyway, so your user space code will now use the device IO control function down here to send the data from kernel land back to user land. So anyway, Kernel-Mode Code, you can use, you can turn on this verbose mode if you have a live kernel debug, and then it will show you every kernel module that loads. And typically, kernel modules should never load unless you're like plugging in new devices or something. So anything that appears is probably the result of malware, pretending a new device is there. Because typically by the time you boot it up, you have all the devices you're going to have. Except for VMware. VMware will keep loading something called kmixture.sys will go in and out. It has to do with whatever VMware is doing. But anyway, that's a fact. So you'll drive object command will show a driver object, and you can see it. And DT will show the structure of the object. So this is, I think, the malicious thing. And anyway, if you trace this thing, when you go into kernel mode, you don't have things like C, D, and E. Those are userland objects. So, and I remember this stuff from the old days of boot.ini files. Your boot.ini file had to refer to which volume to boot from with this strange path, and those are kernel paths. So the kernel path is root of the whole system, DOS devices, then C, then file. That's how you refer to something from the kernel. Because the kernel doesn't have those userland objects like C and D to hang on to. It has to work from the real hardware. All right. So applications work with devices. You'll find the device object in user mode, and then you can follow that to the driver, which is in kernel mode, and you can use these commands to get there. So rootkits are the things that actually use this stuff. A rootkit is going to try and hide in the kernel, and the idea is it's going to be able to have processes running and files on the disk, and they're all hidden from the operating system, so your antivirus can't find them, and your list netstat doesn't show the processes and all that jazz. The most popular thing to do is to modify the kernel and mess with the system service descriptor table, which is very simple. This thing has been around forever. I remember seeing the same thing in the Commodore VIC-20 in the 80s. If you have kernel code, you don't just jump directly to the kernel, because every time you update the kernel, those addresses change, so they make a lookup table that you jump to that has the addresses in the kernel. And in Linux, we've been playing with this in the exploit development class. There's a global offset table, which then jumps to another set of offsets, which then goes in here, because you might update your compiler, and that would change things, or you might update your kernel, and that would change things, and they both have to have a way of a method of indirection, so they can present an apparently unchanged front to the other side. And so then it's really just 2 extra jumps to get there, so it's an extra couple of nanoseconds, and it's worth it to make it possible to maintain the code. So this, in Microsoft's version of it, is the system service descriptor table, and this thing is actually pretty easy to see. All right, this is what Microsoft uses. There used to be 3 ways to access kernel code: syscall, sysenter, and int2e, but now almost all modern code uses sysenter. The others are used by old stuff. So here's ntdil. This is the code that will create a file, nt create file. So at the end, it's going to move the code number, nt create file, then jump, call this where it calls dword pointer, is going to go down here where it moves ESP and EDX and calls sysenter. This sysenter command is the command 0f34 that runs a syscall in Windows. So you now have an SSDT table, and the table is just a whole series of pointers that just point to all these functions: nt create directory, nt create event, on and on it goes. And you can see it live. We'll get there in a minute. But see, if you want to make a rootkit, the simplest thing you do is just change one of these values. And now, every time they try to do something like this one, nt create file, every time they try to create a file, they'll instead go to your malware code, which will then lie to it. Because create file is what you often use if you want to use a file from inside a program. So if you're in Microsoft Word and you say file open and you open a folder, it calls nt create file, and my rootkit will grab it and lie to you about what you see, so you will not see the secret hidden malicious files on the system. You'll just see the other files. So that's the game here. This won't hide the file from dir in the command line, but it'll hide it from some things. And this is the way a lot of early wimpy rootkits worked. Like I used to have a rootkit I used on Linux called Fuck It. And this thing was a Red Hat rootkit from 15 years ago, and all it did was Trojan like 10 system commands. And there were other commands that didn't Trojan. So you do one command and see the malware, another command you won't see the malware, and that's where it starts. You know, the more sophisticated rootkits get smarter. But anyway, see, if you just look at the SSDT, this is all pretty obvious, and that's what I want to do. So lmmnt will show you where the kernel is. So let's start with that. LM, list modules matching NT. Now, according to the book, back in the days of Windows XP, this would actually print out the SSDT, and it doesn't do that anymore, but it does let me see where NT is. So notice, on my machine, NT goes from 824 to 827. So every module in NT should be in that address range. And now there's a longer command that will actually print out the SSDT, which I put here, this mess. Stop that. All right, this thing here is the thing you have to do to see the SSDT. So I don't really understand it, but I don't really care. This is the service table. This is what shows you the pointers. And there they are. These are all the pointers that go into the system. And it's actually very easy to read this thing. Notice how this just counts up by 4s. This is the address of the SSDT entry. Each one of them is 4 bytes long. Here are the bytes. So at this location, CAEC0 is this pointer, which goes to NT trace control. Then 4 bytes later is the next one, which goes to NT translate file path. So these are just counting up. It's just a table, like a file allocation table. And these are pointing to the various addresses. And notice that they're all between 824 and 827, because this is an uncorrupted file. And if I had malware, one of these would be some wildly different number, not inside the NTOS kernel, and you'd spot it. So when you try to do this write file, you'd jump down to some malware, which would do something other than what Microsoft intended it to do. So it's not terribly subtle if you know this much about WinDbg. All right, and there's an example of an SSDT table with a modified entry. They're all 8.0, and this one is F7. So that's a pretty good clue that that's not the legitimate Microsoft pointer that points into NTOS kernel like it should. All right, so you can list open modules. They're all drivers in the kernel, and the malicious driver will be visible. And here's an example of the rootkit hook function. Here's where it goes. It jumps first it jumps to the original NT create file, and then for some requests, and for other requests, it jumps to something that won't show it to you. So it has a list of files to hide, and it lies about them, and the rest of the operating system, it just calls the original function to let you see your machine working correctly for most cases. And then there's interrupts out there too, in case your hardware wants to request immediate service, and these have, your driver will register a handler for an interrupt code, and this makes an interrupt service routine, and there's an interrupt descriptor table that has the pointers to all the interrupt routines. This is like the kernel mode of the structured exception handler we talked about before. All these are interrupts, not exceptions, and you can see that with bang IDT. Let's take a look at that. Bang IDT. And there's the interrupt descriptor table. So here's the USB port interrupt service and so on. So here are some signals, I think, the types of interrupts, and here's the code it'll jump to. So there's just a long thing, HAL broadcast service and so on. There's a bunch of things where the hardware might decide it needs immediate. It's not that big a table. It's a lot smaller than the SSDT. All right. And there's an example of that. All right. So this shows you where they're all going, and they should all be going to named Microsoft things or things put in there by device drivers, and you might look for unnamed or unsigned things as a clue that it's malicious hooking here. So if you do want to load a driver to test it, you can't run a driver load. Remember, when you wanted to load DILs in OllyDbg, there was a special program to add the exe part so you could run it. And this is the thing, OSR driver loader is the special thing to load a driver. So you can test a driver because drivers do not run themselves. So that's a product there. And of course, everything I'm talking about is 32 bits. So the 64-bit version, there's 2 issues. The first thing, of course, is you have to use bcdedit instead of boot.ini, which you know. But the much tougher version is Microsoft is really getting fed up with lousy drivers. I mean, something like 80% of all the blue screens of death come from poorly written drivers. They're written by people that make cheap hardware in other countries, and Microsoft has no control of them. So what they're doing is they're making it more and more difficult to run crappy drivers in the kernel. And so the x64 all have patch guard, which means no third-party code can mess with stuff like the SSDT or the IDT anymore, and all the drivers have to be signed. And so, it's an issue. It can affect debugging. You have to get special 64-bit kernel debugging tools if you want to get past that limitation, apparently. And all right, and Microsoft now enforces driver signing. On all 64-bit versions, and certainly all server versions of their operating system, every driver should be signed, and Microsoft would like you to verify the signature with the company that signed it, so you know who wrote it is really a reputable company, and you know it hasn't been altered. That's the idea. It is possible to turn off driver signing if you want to, because you're really determined to use some old crappy cheap hardware. And you can do it here, but Microsoft makes it difficult because they really don't want you calling them and whining when everything crashes on your cheap crappy hardware. If they want you to use drivers that are certified to run on that version of Windows, which means Microsoft tested them and made sure they passed certain rules of sanity to not kill the OS, which is reasonable because they've been getting blamed for machines are dead for a decade or more, and it's not really their fault.
Oh, that's a security issue.
Well, you could argue. Anyway, it's other people's code, and so the only thing they might call their fault is they didn't limit what other people could do more, and now they're doing that. Anyway, all right, so there's the last batch of iClickers.
Like a blacklist, you send them a driver, and so Microsoft says, we hate this company, we hate this driver.
Well, see, I think, remember, Microsoft is all about money. So that would just irritate people. What they have is the opposite, the carrot instead of the stick. You get to put this logo, designed for Windows Vista, and hopefully people will pay another $10 for your NIC. And the other guys just don't get to put the logo on there, which is Microsoft's subtle hint, don't buy this cheap junk. Anyway, so that makes more sense. It's also more money for them.
You can cheat sometimes if it's made by the same chipset for a network card, for example. You can use someone else's driver and it'll still work.
Oh, you can, but don't call Microsoft for help. Anyway, so which module is loaded and unloaded by virtual machines? Which might confuse you. Well, there's a bunch of tricks to make the wrong driver run, but Microsoft is not going to love you for doing it.
I think there's 6 ways to load a driver.
Oh, yeah, I remember this. Yeah. But there's a lot of ways to use the wrong driver, too. You do a lot of evil things with drivers, but they all increase system instability. All right, anyway, this is KMixer. I don't know what it does. It might be fun to Google and find out what the heck it's doing. Virtual machines are actually very sophisticated because we heard this from one of the speakers. VMware first came out, their machines cut 40% of the performance off. And they said, no one's ever going to use this, and so they greatly improved them to where it's almost as fast as being on the bare metal, and that's when people really started taking it seriously. And there's a bunch of real sophisticated stuff going on at the low level to make that happen. Anyway.
They can make it better. Make a memory card on a PCI slot, and then reserve that for virtual machines or something.
Yeah, and now they have hardware-assisted virtualization, which is the big step forward. Now the hardware helps. Anyway, sorry, what's the normal function used to execute kernel code? In Linux, it was int 80, I think. All right, quit at 35. It's sysenter on Windows machines now. It's not syscall, is it? I think it's sysenter. Let me go back and see if I'm lying to you. There. Sysenter is the modern solution. Syscall is one of the old ones. You can always remember it because syscall is what it is. That's what everyone calls it. So Microsoft uses the wrong name. That's the general rule. It's a sys. It's a sys. That's right. That's exactly it. Everything in Microsoft is always named the wrong name, and you can remember it that way. It'll help you a lot. It's a good mnemonic. Anyway, so. I don't know why that happens, but it's really very, very complicated is probably how this ends up. Anyway, so what's the most commonly altered thing by rootkits? That's the easiest way to make a kernel mode rootkit. And it totally would have worked on the Commodore VIC-20, I'm telling you, anyway.
Don't you miss the good old days when the RRT was your biggest problem?
Not really, no. What's amazing is what I learned then still counts. The 8-bit assembler I learned is pretty much still what you do.
You know how many IO addresses you had or how many RRTs you had?
It was very simple, like 8 interrupts and only 8.
And the limitations.
Only 1K of RAM and stuff, but the same principles are the same. So SSDT, the system, service system, or whatever it is, descriptor table, that's where you typically hook things. All right. Which one of these is not used in Windows 10? All right, I'll quit at 30. All right, that's boot done any. It has gone the way of autoexec.bat. These old-fashioned text-based configuration files are not used anymore. All right. If you want to use an unsigned device driver in 64-bit Windows, what do you have to do? And I guess I should update my slide. All right, there you go.
pointed though, like you were saying how so much stuff is still relevant for what you learned, and then show the next slide of how it's completely irrelevant nowadays.
There's a few things that go away, but then they come back another way.
Boot in it, though?
Like in Linux, there's all these text-based configuration files.
That actually,
That's starting to go away with SysMD.
Anyway, there's no integrity, is what you need. No integrity check. You set a switch. That's yeah. You do it in the kernel.
Switch in bcdedit?
Oh, you disable. It is in bcdedit, but that's right. However, here's my argument. You have two answers. Like one is the big container, and one is the more specific container. So bcdedit has some truth, but this is the more specific answer. That's my argument. I'm willing to entertain
What does the book say?
complaints. Well, the book doesn't tell you how badly my question is written. I mean,
So I wasn't thinking.
it's a question. Anyway, I think I'm going to stick with it on this one, but you're right to complain. Sometimes you win. Anyway, let me knock off the recording, and we'll see who won. So this is going to be kernel